Today we're going to talk a lot about convergence tests for our infinite series. Now, we already know that an infinite series, if it's going to converge, will converge to the limit of its partial sums. So recall, if a series sum from 1 to infinity of an converges, it converges to the limit as n approaches infinity of Sn, the limit of its partial sums, where Sn is just the first n terms of our series added up. So this comes in handy if we can actually find a formula for our Sn. Then we just take a limit of that and figure out if the series converges or diverges. The problem is finding this partial sum can sometimes be incredibly difficult. So we're going to learn over the next couple of videos a couple different ways to check if our series converges or diverges without even needing to figure out what the partial sum formula is. But before we learn these new tests, let's just do this partial sum thing one more time. We're going to learn whether a particular series called the harmonic series converges or diverges by using its partial sums. So, an example. Does the harmonic series which is the sum from 1 to infinity of 1 over n, converge or diverge? And what we're going to do is we're going to look at some of the partial sums. Now, we are going to be kind of sneaky and kind of clever here. We're not going to look at every single possible partial sum. I'm going to look at very particular partial sums. So I'm going to look at partial sums S2, S4, S8, S16. I'm going to come up with some sort of cool pattern so we can see what's going on here. All right, so let's look at S2 first. Remember, our partial sum S2 is going to be the sum of the series just from 1 to 2. So this would be a 1 over 1, which is 1, plus a 1 over 2. Now, yes, I know that this happens to be equal to 3/2, but I'm just going to leave it like this because I'm trying to look for patterns and things, so I don't know how much I want to simplify yet at this point. So S2 is 1 plus 1/2. What's S4? Well, S4 is going to be the sum of the first 4 terms. 1, 1/2, 1/3, and 1/4. And now here, this is where the sneaky clever stuff comes in. I am going to say, rather than simplifying this, I'm just going to notice that this happens to be a number that's bigger than 1 plus 1/2 plus 1/4 plus 1/4. Well, that's true. I mean, 1/3 is bigger than 1/4, and the rest of the terms are all the same. So yes, S4 is larger than this. But why in the world am I doing this crazy thing? Well, because 1/2 plus 1/4 plus 1/4 is equal to 1. And another way to write that is 2 over 2. We don't normally write 1 that way, but there's a reason I'm doing this. Now I have S2 equals 1 plus 1 over 2. S4 is larger than 1 plus 2 over 2. Kind of getting a pattern going. Let's look at S8. S8 is the sum of the first 8 terms. 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, and 1/8. That's a pretty big mess there, but I'm going to use the same trick that I just did with S4. I already know that S8 is bigger than 1 plus 1/2, 1/4, and 1/4. And now for the rest of these guys, 1/5, 1/6, 1/7, those are all larger than 1/8. So I can say that this is greater than 1/8, 1/8, 1/8, 1/8. And again, why am I doing this? Well, because I already know what's going to happen on this, and this is a super slick way to show whether the harmonic series converges or diverges. So what I have here now is 1 plus 1/2, 1/4, and 1/4 is a 1. And 4 of these 1/8 is another half. So I have 1 plus 1.5. Well, that's the same thing as 1 plus 3/2. Interesting. So S2, 1/1, 1 plus 1/2. S4, 1 plus 2/2. S8, 1 plus 3/2. We have a pattern going. Notice I have powers of 2 for the partial sums, and those powers are becoming the numerator in that fraction. So similarly, if I did the same procedure, I'm going to get S16 is greater than 1 plus 4/2. My next power of 2 is 32. S32 will be bigger than 1 plus 5/2. And in general, I get that Sn is going to be greater than 1 plus n/2. And I'm sorry, not Sn, S sub 2 to the n, my powers of 2. S sub 2 to the n is going to be larger than 1 plus n/2. That's the pattern that I've discovered. So now if I take the limit of these particular partial sums, I take the limit as n approaches infinity of this S sub 2 to the n, I get the limit, this is greater than the limit as n goes to infinity of 1 plus n/2. And what happens to this limit as n approaches infinity? Well, huge numbers divided by 2 are still huge. This limit goes to infinity. So what I'm saying here is that the limit of my partial sums will also be infinity. What does that mean? That means that my series diverges because the limit of my partial sums diverges. So the series sum from 1 to infinity of 1/n diverges. This again was called the harmonic series, and it's divergent. Now this is actually kind of great because now we have a very special series, this harmonic series, and every single time you see this harmonic series, you already know it's going to be divergent. You don't have to do all this work anymore. You know it because we already did it. It is a divergent series. So now the question is, what do we do if we have something even more complicated? Like, this was already pretty clever. I didn't just find my regular old partial sums. I found very particular partial sums using my powers of 2. What if it's even harder to do that? What if I can't come up with some pattern to write my partial sums in a way that I can take the limit? That's where all of our tests for convergence come in. So our first test that we're going to learn today is actually called the test for divergence. Now, my test for divergence states that if the limit as n approaches infinity of a sequence AN does not exist, or if the limit as n approaches infinity of AN exists, but it happens to not be 0, then the series given by adding up these terms of the sequence diverges. Notice though that this is a very, very particular statement. This is saying if you ignore the part in front here telling you to add all these terms up and just take the limit of the AN, if you get any number other than 0, or if you get that the limit does not exist, the series diverges. But it does not tell you that if you get 0 that the series converges. If I happen to get 0 for this limit, this test for divergence tells me absolutely nothing. If I get 0 for that limit, my series could converge, my series could diverge. We have no idea. You would have to use a different technique. The good news though is this test for divergence is usually pretty quick. So I would suggest you take a look at it each time you have to determine if a series converges or diverges, because if it does diverge, you get the answer super quick and you're done. So let's do an example of this. So we are going to show that the series sum from 1 to infinity of n squared over 5n squared plus 4 diverges. And I'm going to use my test for divergence to do this. So what I have to do is take a look at what happens as my n approaches infinity, and I look at just the sequence of terms that I would be adding in my series. So let's look at the limit as n goes to infinity of my an. So that's n squared over 5n squared plus 4. And figure out what this limit is. Well, if I look at what I have here, I have degree 2 on the top and on the bottom. They have the same degree. That means I know this limit as n approaches infinity is going to the ratio of those coefficients. This limit is going to be 1/5. Now, what does that tell us? Well, my test for divergence says if I do this limit and I get anything other than 0, then my series diverges. And 1/5 is definitely not 0. So this means by the test for divergence, this tells me that my series diverges. See, that's what I was saying. This test is super quick as long as you get something that's not 0. Unfortunately, if you get something that is 0, we have no idea what the answer is and you got to start all over with something different. But this is super quick, so you might as well try it, because if you get a number other than 0, or you get the limit does not exist, you're done. So it's not that bad. I would like to point out that that harmonic series that we just worked with before this, that was the series of 1 over n. If I take the limit of 1 over n, I get 0. Test for divergence tells me absolutely nothing. We already know the harmonic series diverges because we did it earlier in the video, but the test for divergence would be useless on that particular problem. All right, so let's talk about some properties of our series, some things that are super nice and that we can use to help us figure out if series converge or diverge. So as a theorem, I'm going to write that if I have 2 convergent series, and if C is a constant, then I have a couple of true things. First, the sum of C times one of my series, AN, I can pull that C out in front of the sum and get another convergent series. Also, if I have a sum of AN plus or minus BN, I can split this sum into two different sums. The sum of AN plus or minus the sum of BN, and it's still going to be convergent. Be careful. Remember, this theorem is only for convergent series. If you have divergent series, you're not going to get these conclusions, so be very careful. Remember, when applying a theorem to a problem, you need to make sure all the conditions are met before you use the theorem. Something else that's super nice about series is that a finite number of terms does not affect the convergence or the divergence of the series. So here's just a little note for us. A finite number of terms does not affect convergence. What I mean by that is if the sum from 1 to infinity converges, well, then so does the sum from any other number, I'm just going to call it capital N, to infinity. So if you know the entire series converges, well then you can take just the end of the series, still going to infinity, but starting at a different number, and it's also going to converge. More importantly, this works the other way as well. If you happen to know that the sum from some number to infinity converges, well, then so does the sum from 1 to infinity. All the differences between those two series is just a finite number of terms. If this guy is already finite and I just add some finite number of terms to it, you're still going to have something finite. That's all that this is saying. All right, so far, doesn't seem too terrible. All we really know right now is the test for divergence and the definition of what it means to converge. Now we get into some of the trickier things. The next test we need to learn is the integral test. Now, the integral test, in a way, is kind of nice because, hey, we're in Calc 2 right now. What have we been doing all of this time in Calc 2? We've been integrating. So the integral test is a way to rewrite a series and figure out if it converges or diverges by using something we're familiar with, an integral. So that happens to be very nice. Here is our integral test. The integral test says, suppose that f is a positive, continuous, and decreasing function on the interval 1 to infinity. So I have a continuous function, it's positive, the terms are getting smaller and smaller, it's decreasing. Then I have two facts. One, if the integral, the improper integral from 1 to infinity of f of x converges, well, then so does the sum from 1 to infinity of an, where an is equal to my function when I plug an integer into it. So what I'm saying here is that my function is a nice continuous function, but if I just look at the integer values, if that equals the terms of my series, then convergence of the integral tells me the series also converges. Similarly, if the improper integral diverges, so does my sum. All right, not too bad. So this is saying, hey, if you can rewrite your problem with a series, write it using a function instead, you can take the integral, figure out if that improper integral converges or diverges, and it tells you about the original series. Pretty cool. Now, Calc 2 in general is a very difficult course to learn, not because the material is necessarily terrible, but just because you don't know what technique to use all the time. And that's what we're going to hit a lot in the next couple of videos. You're going to have quite a few different tests to see if an integral or see if a series converges or diverges, but you're not going to necessarily know what test is the best one to use. And I'll try to guide you as best I can, but unfortunately, just like almost everything in Calc 2, what you got to do is just pick a test, go with it, probably fail, throw it out and try another one until you build up that mathematical instinct of what test is a good test to use. So we're going to do an example using this integral test, and I'm going to explain why I think an integral test would be good to use on the particular problem. So, an example. Does the series from 1 to infinity of natural log of n over n converge or diverge? So why am I going to use the integral test on this problem other than the fact that we just talked about the integral test? Well, my instinct when I look at this problem, I see natural log of n over n, and I think to myself, hey, if this were a function, natural log of x over x, I could integrate that guy really easily. It's just an integral using a u substitution. U equals natural log of x, boom, simple u sub, we're done. So if you look at your series and it just jumps out to you as, I know how to integrate that, integral test might be the way to go. So I'm going to use that integral test. But I have to be very, very careful. Before we can use this integral test, we need to make sure all of the conditions of the test are met. So first, let me write down the function that we would be integrating. Natural log of x over x. In order to use the integral test, this function needs to be positive, it needs to be continuous, and it needs to be decreasing. Now, the positive and the continuous part is not so bad because I'm only considering from 1 to infinity. As long as I'm bigger than 1, this guy's going to be continuous, it's going to be positive, not a big deal. So finding that it's positive and continuous is not that bad. So I have that. The question is this function decreasing? And now here's the kind of tricky part. Yes, I know the integral test stated that we needed to have the function decreasing on the interval 1 to infinity. That's not actually true. It just needs to be decreasing eventually. So as long as you can show that your function at some point becomes a decreasing function and stays a decreasing function for the rest of the time, then you can use the integral test. So let's figure out if this is decreasing or not. And how do we do that? Well, we remember back to Calc 1. Calc 1, figuring out if a function is decreasing or increasing, you look at the derivative of the function. If the derivative is negative, you're decreasing. Derivative is positive, you're increasing. So let's look at the derivative. So I had f of x is natural log of x over x. If I'm going to take the derivative of this guy, I need a quotient rule. So my quotient rule, you guys might remember, is talked about as being the bottom times the derivative of the top minus times derivative of the bottom over the bottom squared, and it's terrible to memorize. Well, I remember it as this is high, this is low, and my derivative becomes low d high minus high d low. Square the bottom, and away we go. Where when I say d high and d low, I'm talking about the derivative of the top and the derivative of the bottom. So all we have to do to fill in the pieces is figure out derivative of the top. Derivative of natural log of x is 1 over x. And derivative of the bottom, derivative of x is 1. And there's my derivative using the quotient rule. But I can simplify this. My derivative is equal to x times 1 over x is 1. And then I have a minus natural log of x. And this is over x squared. And I still want to figure out, is my function increasing or is my function decreasing? I want it to be decreasing. So I want this guy here to be less than 0 so that my function is decreasing. So I have to figure out, when is this derivative less than 0? And the first thing I want to point out is this denominator is not affecting anything here. X squared is going to be positive. So whether this whole thing is positive or negative depends on the numerator. So to solve when this is less than 0, I just need to figure out when is 1 minus natural log of x less than 0. And to solve that, just add the natural log of x to the other side. 1 is less than natural log of x, which to solve that, we just have to rewrite it as an exponential. And I get that e is less than x. So what this is telling me is my function is decreasing as long as my x values are larger than e. So it's decreasing eventually and decreases from that point on. So my function is decreasing when x is larger than e. This means that, yes, I had a positive, continuous, and ultimately decreasing function. So yes, I can use my integral test. All right, so let's do it. The integral test says, let's look at the integral from 1 to infinity of my function. And just like with any improper integral, the first thing you have to do is rewrite this as a limit. This is the limit as t approaches infinity, the integral from 1 to t of natural log of x over x dx. Now to actually calculate this integral, that's where the u substitution comes in that I was talking about. We're going to have u equals natural log of x, which means du is 1 over x dx. And that is just beautiful because I have a u on the top, 1 over x dx would be my du. This is just an integral of u du, no problem at all. So I have a limit as t approaches infinity, integral from x equals 1 to x equals t of u du. I decided not to change my bounds on this integral, but I am specifying to myself that my bounds are x values and not u values. So I make sure I put this back in terms of x before I plug my numbers in. So the antiderivative of u, using our power rule, is going to be a 1/2 u squared. So now my limit is a limit as t goes to infinity of a 1/2 a u squared, And my values are x equals 1 to x equals t. Plug our u back in to get the limit, t goes to infinity, of 1/2 natural log of x squared from x equals 1 to t. Now all I have to do is plug in those bounds, take my limit, and see what happens. So I have a limit, t goes to infinity, of 1/2 natural log of t squared minus 1/2 natural log of 1 squared. Now, natural log of 1 is 0, so this whole last term is just 0. I don't have to worry about it. I just have to check this piece right here. Now, as my t approaches infinity, my natural log function also grows to infinity. Remember that your natural log function, the graph of it, looks something like that. As I go to infinity, I am going up infinitely. It just goes kind of slow, but it will get there eventually. So that just means that this limit, my natural log approaches infinity, I'm squaring it. Doesn't even matter that I'm chopping it in half. This limit is infinite. And now what does that mean? Well, by my integral test, this tells me that since I got infinity on my improper integral, my integral diverged, and so my series, natural log of n over n, also diverges. Not so bad. It's nice when our math builds on the stuff we've already done. Improper integrals, not a big deal. Now I can use them to determine whether a series converges or diverges. But of course, sometimes the integral test is not the best way to go. And we will learn many more tests that we can use in those sorts of situations. But maybe you really like the integral test. And if you're really, really good at integrating and your series is something that you can integrate, go ahead and use the integral test. That's just fine. All right. So that was our integral test. And now all that we have to do to finish up the rest of this section is talk about a very special series called the P-series. And we're going to talk about when the P-series converges or diverges. So, P-series. A P-series is of the form sum from 1 to infinity of 1 over n to the p. And this P-series is super nice. It's going to converge when my p is larger than 1, and it diverges when my p is in between 0 and 1, including 1 itself. And we're going to show why this is true. So first, let's just assume right now that p is not 1. If p is not 1, then I can use the integral test on this guy and integrate the function 1 over x to the p. So using the integral test, I have an integral from 1 to infinity of 1 over x to the p dx. And as always, rewrite this using a limit right away. I'm also going to rewrite my 1 over x to the p as x to the negative p power, just because that works better for me for integrating and using the power rule. I can use the power rule on this problem because I'm assuming that p is not equal to 1. So using my power rule, we get a limit as t approaches infinity of my x to the negative p plus 1 over negative p plus 1, and I'm plugging in t, and I'm plugging in 1. So what is this equal to? Well, let's plug in the t and plug in the 1. It's not going to be anything too exciting. I have a limit as t goes to infinity of my t to the negative p plus 1 over negative p plus 1 minus my 1 to the negative p plus 1 over negative p plus 1. So now I have to be very careful here. This is true so far, but all we've done so far is just assume that my p is not 1. P could be bigger than 1 or p could be less than 1. And different things happen each time. So let's look now, if p is larger than 1, what happens to this limit? If p is larger than 1, well then a negative p plus 1 is going to be a negative number. That means that this guy can move down into the denominator, and my limit is going to end up being a 0 for that, and the entire limit will just be equal to this guy over here. So since p is bigger than 1, I have a negative exponent on my t. As t goes to infinity, this first term goes to 0, and I get that the limit is equal to negative 1 to the negative p plus 1 over negative p plus 1, which converges. By the integral test. So the integral converged, and so the series converges if p is larger than 1. Now, what if p is less than 1? So if my p was in between 0 and 1, well, then this guy here, that exponent on my t, ends up being a positive number. And as I have my t approaching infinity, a really huge number to a positive power is going to blow up to infinity. So I get that my limit is infinite, which means that the integral diverges, and so the series also diverges by the integral test. All right, so I've shown most of the cases now. I've shown that if my p is bigger than 1, my p-series converges. And if my, right there, if my p is between 0 and 1, my integral test says it diverges. But what about if p is equal to 1? Remember, it was right here before I erased it. Before I actually did this integral test, I assumed that p was not 1. So all I have to do to finish this up is check, what if p is 1? Well, if p is 1, well then my sum, my series here, n equals 1 to infinity, 1 over n to the p, is equal to the sum from 1 to infinity, 1 over n. And what's that? That's our old friend, the harmonic series. And we showed at the very beginning of this video, we showed that this harmonic series diverges. And so we've now shown all of the possibilities that we listed. Our p-series, sum from 1 to infinity, 1 over n to the p. It converges if p is bigger than 1, and it diverges if p is between 0 and 1, including 1 itself. So that's all I have for you for this video today. On our next video, we'll learn some other integration technique, or not integration techniques, other tests for convergence and divergence of series. And it's going to be pretty complicated trying to figure out what test is the best test to use and what test I should avoid in certain circumstances. And it can be pretty difficult. So I hope you stick with me and keep learning all of these tests. If you have any questions, feel free to drop them below, and I'll get back to them as quickly as I can. If you are one of my current students live in my class, you can also come to me with questions in office hours. Thank you all for watching, and I will see you on the next video.